We are in the fourth video on sequences. In the last video, we were talking about the idea of converging or diverging sequences. We also touched on the squeeze theorem. Let's talk a little bit more about converging sequences. We'll first need bounded, this notion of a bounded sequence. We'll say that a sequence can be bounded above or below. Sequence is bounded above if all of the terms never get bigger than some value capital M. Likewise, it's bounded below if all of the terms never drop below some small value M. We'll simply say that the sequence is bounded if the sequence is both bounded above and bounded below. Good. Here's a nice fact that sequences which converge are bounded. Take a look at an example to motivate that. Let's take 1 over the index and then either plus or minus. Okay, so if we take an index of 1, let's start with positive 1, then an index of 2, get negative 1/2, index of 3, get positive 1/3, and so forth. These terms of the sequence never go above m equaling 1, nor do they drop below m equaling negative 1/2. They're always trapped between these two values. It's bounded. The sequence is bounded. More importantly, this one is a convergent sequence. This converges to 0. So the fact was convergent sequences are bounded. Good. So this is the first notion, bounded. We need a second notion, monotone. So let's look at monotone. First, let's talk about monotone increasing, monotone decreasing. So monotone increasing, and we're going to say increasing for all terms after some starting term. So increasing if the next term is bigger than the current term. And that only needs to happen after some given index. But once you find that index, then thereafter, all successive terms are bigger than the current term. Likewise, the sequence will be decreasing after some m naught if any index after that n naught has the next term being smaller than or equal to the current term. And then if either one of these two conditions hold, we can simply say monotone. So if it's increasing after an n naught, or if it's decreasing after some n naught, we can simply say monotone. All right, so now we want to state MCT, monotone convergence theorem. We require that every single term in the sequence is bounded. So that's both above and below. And then if we look far enough out in the sequence, every term thereafter has the behavior of being monotone. So it's either increasing or it's decreasing. So the first part is the terms are bounded, they're trapped within this region. And then the second part is that it's monotone, so maybe always going up. Well, if it's always going up and bounded above, it's got nowhere to go, it must converge. So that's MCT. Good. So this is a very important tool for us. And let's take a look at one application. So let's take this sequence. You have n copies of 4 in the numerator, and then n factorial in the bottom. N factorial is a product of n integers. Compared with n integers on top, well, each integer on top is the value 4, and once n surpasses 3, then those denominators are going to outstrip the numerator. So it looks like this should converge to 0. But we want to establish that rigorously, and we're going to use MCT. Take a look at the first term, second term. Oh, that's increasing. But then here we go on the third term, and then the fourth term. There's no change from third to fourth, and then it starts to decrease. We can cheat a little bit and take a look at a graph. And here is a function 4 to the x over x factorial plotted, and then picking out at integer values. All right, that's just a visual motivation. So if we want to apply MCT, we need that it is bounded and monotone. Let's address that second point, monotone. Write down the next term. Here's the definition of the nth term. Write down the next term. So you're going to need 4 to the n plus 1, which can equally be written out as 4 to the n times one more copy of 4. Down in the bottom, you'll need n plus 1 factorial, but that's the same thing as n plus 1 times n factorial. Breaking it up in this fashion, we can take this 4 over n plus 1, multiplying 4 to the n over n factorial, but that's exactly a sub n. And provided that n is bigger than or equal to 3, this quantity will be less than 1, hence the product will be less than one of the factors. Thus, this establishes that the sequence is decreasing for n greater than or equal to 3. Good. Now, MCT requires two things. We, looking at that inequality, showed that it is decreasing, i.e. monotone, after n bigger than or equal to 3. On the other hand, it is bounded above by looking at the first few terms, and then thereafter by being decreasing, we know that it's bounded above. And then secondly, it's bounded below because you have a quotient of positive and positive, so it's bounded below by 0. MCT requires that it be bounded and monotone, and thus it will converge. Good. Now that we know that the sequence 4 to the n over n factorial converges, we could note that if we look at terms of the sequence, it will converge. But if we look at the n plus first term, it's also going to converge to the same limit. They're the same sequence. On the other hand, saying that the n plus first terms will converge to L, concentrating on the n plus first term, breaking it up like we did before as a product of two terms, using our limit laws, we can distribute lim to this factor, lim to that factor. This limit clearly exists as 0, and this limit exists by MCT. Write that out as a product, 0 times L. That's simple. That's just 0. Thus, our initial assumption of n copies of 4 on the top going up against n copies of integers in the bottom, but the bottom integers may grow arbitrarily large, the top is going to lose. And therefore, the overall quotient will become small. So this was applying the monotone convergence theorem. Here's a nice challenge. Same notion. Use MCT to show that the sequence converges to this capital L value, where the sequence has this definition, or this pattern. First term rad2, second term rad2, the radical of 2 times rad2. Third term, the radical of 2 times the radical of 2 rad2. Okay, so it's a nesting pattern. All right, well, you know to apply MCT, you need 2 things. You need that it is bounded. And in this case, you want to show that it is monotone increasing. Excellent. There's a nice challenge for you.